So the first thing I want to say is, NVMe has become quite a diverse ecosystem, right? It's even though a lot of the features we talk about are, kind of on the towards the left, historically towards the left side of this diagram, we're seeing now, and we've heard about it today, features for boot, features for low power. We're even starting to see people even integrate or build cards, like the Compact Flash announced a CFX spec where they're going to put NVMe PCIe in a card that will go into a high-end camera. I've heard of NVMe kind of devices flying around in drones, so I don't know, it could be, I don't know, that's a way to compete with our fellow standards or something. So there's a broad diversity of platforms. And it's also, to layer on top of that, we're getting, we've branched into non-PCIe fabrics, so we're in a much broader environment when we talk fabrics, and there is out-of-band management, which has its own set of nuances and things to worry about. So, we can't boil the ocean and solve all security problems, but we're working on some of them. So the threat classes, as we've kind of discussed them, are in two big buckets. The first threat class is just physical device access. Somebody actually either gets a hold of a drive and takes it, or gets a hold of a device and takes it, or if you want to repurpose a device like your phone, right, or a tablet or something like that, and you want to make sure that it's really clean of any confidential data. The other main class, which encompasses a bunch of things, and some people will do this taxonomy differently, but this is how we thought it made sense. So there's data access, so theft or unauthorized disclosure of data, either for theft, whether it's emails or things that Jeremy was talking about, or malicious or criminal change or destruction of data, denial of service attacks where people brick a device by modifying code. So there's a variety of mitigation strategies that we think fit these threats. So for the physical access, doing things like having sanitized device, data at rest encryption, and just device locking is a way to prevent, is a method to attack the first threat. If somebody just steals your phone and it's locked and encrypted, they can't do anything with the data, ostensibly. For data access, you can use these previous categories of protection, but there's also some other ones like media right protection, data in flight protection, and end-to-end crypto integrity checks. And then finally, and importantly, there's another category of mitigation, which is authentication and access. Because I'll give you the example. You could have write protection for the device. You could allow write protected namespaces for NVMe, and somebody could permanently write protect partition or a namespace. If you don't have a way to authenticate the entity that's allowed to do that, they can brick your device. So you need, for all of these things in the middle column, we need authentication and access control at various levels. Now, where we've been working is that NVMe, so for sanitized, NVMe and TCG both have solutions for the NVMe ecosystem. Data at rest encryption is covered by TCG and also device locking. The write protection is kind of covered by both, and there's some reasons why we need to do, have some in TCG and some in NVMe. And then the authentication and control mechanisms also kind of span the two specs. The data in flight and end-to-end are kind of outside the scope of the interface specs. We'd see that more like in IPsec or higher layer protocols. So we're not doing any. The work is being done in other bodies. So we're not building these capabilities or need to, or we don't think we need to into NVMe. So let me talk first about TCG and how we've been working together and what we've done. So kind of before we started working together, the TCG looked like this. It had an Opal solution for client, basically, and it had an enterprise solution, enterprise SSC for enterprise. They had somewhat different features and different approaches to the problem. And so the first thing we did together was we added a binding so that you could use for this, you need a binding for each interface that you're using. So we did a binding for NVMe in the sys spec so that you could use Opal or Enterprise SSC with an NVMe device, just low-level binding. Then we did, and this work that began progressing here, so we did Opal Lite next, and which is a slightly de-featured Opal. It's just lower overhead, smaller tables, for client. It was kind of client focused, so we reoriented the features. And finally, we did Pyrite, which is just a device locking with no encryption. So Opal Lite still has encryption, Opal has encryption. So this family here, what we did, we had, and then lastly, we added what we call configurable namespace locking, which is an NVMe specific feature to the Opal family. Now, even though NVMe spans enterprise to client and mobile, most of this work in the Opal family really kind of related to client. The demand was coming from there, and people didn't really want to change the enterprise environment at the time. So what happened was the enterprise environment kind of stayed static. We developed a new core spec, and so the Opal family has become pretty well suited to NVMe, but there is a gap, and the gap is that we want a solution that supports NVMe and addresses enterprise use cases, but is built on the current and updated version of the core spec. So this is kind of inside baseball in terms of how it works, but it's important to enable developers to build an integrated solution on one core spec. So we're in discussion with TCG on how we fill, what do we fill this gap with? Is it another SSC? Is it some other reformatting of the Opal family specs? But in the end, we think we'll have an Opal family solution that covers enterprise SSC use cases that can be used for NVMe. And that way, the NVMe ecosystem has kind of one security infrastructure rather than two with respect to TCG. So SATA and SAS will keep using enterprise SSC, and unless they want to change. But so far, they seem to want to stay where they are. It works. Don't fix it. So that's the TCG story for now. Now, as far as native security features in NVMe, there's 4 main ones that we've put in. So the first is just an infrastructure piece. So we have security send and receive commands in NVMe, which allow you to tunnel commands of any other security protocol through the interface. So you can tunnel TCG protocols, you could tunnel anything. They're just commands that you load them up with the packet you want, and they're special administrative commands. So the tunneling mechanism works, and that's the basic mechanism for integrating TCG today. We just, as Lee was talking about, we added namespace write protect, where it's going to be a 1.4 future feature. The proposal is underway, and it allows a device or it allows the host to set various states, either no write protect, simple no write protect, or write protect until reset, or even permanent write protect, and which is a kind of a scary feature, but there are some platforms that really want to do that. And the key to these red states here, the write protect until reset, is that they're key for a secure boot or something like that, where you want to make sure that the firmware or software hasn't been tampered with, or the boot image that's sitting on the drive. The other thing we have in the spec today as of 1.3 is sanitized device. I won't recover it because people have already talked about it. And then the third building block, or the fourth building block we put in NVMe, is this replay protected memory block, which is basically the authentication mechanism. It allows, so for things like, if we want to make sure that permanent write protect can be disabled, we want to make sure that the OS set permanent write protect or set write protect until reset when it booted, but it doesn't want anybody else to be able to do it. It uses RPMB as a way to have an authenticated way to make sure that the privileged OS is the only entity that can use these commands. So RPMB is the building block we use for that. And the other thing, security-wise, that's being discussed between TCG and NVMe is in-band authentication for NVMe over fabrics. So without going into all the details here, essentially when we establish a connection from an initiator to a target, we want to be able to, right now there is no real secure mechanism of doing that. Administrators and data centers deal with that the way they, however they choose to. We want to build some protocol into the spec that allows an initiator to be authenticated to the target. So we're not quite sure where that work lives, whether it's native in NVMe or if it's TCG. So we're discussing where the best place to do it. So in summary, NVMe and TCG have worked together on setting up a set of baseline features, and we're continuing to work together, in particular on a new data, that gap I showed you before, the data at rest solution for NVMe that pulls in enterprise SSC needs, and it's built on the new core spec. And we're working on the NVMe over Fabrics authentication, and there may be other things that come up. It's an ongoing process. So we hope that those interested will get involved both in NVMe and especially in TCG, because it's not, NVMe community can say, I want this and that to happen in TCG, but we need member companies to come to TCG and help us drive the spec at TCG for those parts of the solution that TCG develops. So that's all I've got.